as you know, this is the last Compton lecture for the fall, and I wanted to just make a couple of comments before Philip begins with the lectures. The first thing I wanted to do was to thank Philip for what's been a really fantastic lecture series. And I also wanted to thank Mary Heinz, who all of you have met, and she's the one who makes all of this run smoothly. So let's thank Mary. She's up in the back. Thanks, Mary. So two other important things. One, I think many of you know there's lunch after the lecture today upstairs in room 206, so I hope many of you will be able to stay and join us. And the other thing is to assure you there will be a lecture series in the spring. We have a speaker, and you should get an announcement about it, I think in the next few weeks. So I hope you'll join us for that as well. So Philip, please.
Wonderful. Okay, good morning. One more time. Last time, we witnessed the rise of radioactivity. We saw how it all started with Henri Becquerel's sort of serendipitous discovery of there being a new kind of rays being emitted from uranium minerals. We then see how the Curie dream team, Marie and Pierre, went after the sources of these rays, and they found two new chemical elements. First, polonium, named after her native country of Poland, and then radium, named after its very intense radiation. And then by 1903, just a few years after that initial discovery, in fact, we had the scheme of classification that today we associate with radioactivity. It was a lot more complex than what people thought at the beginning. There was 3 different kinds of rays than just one. There was alpha radiation, positively charged and very easy to shield. There was beta radiation, negatively charged and a lot more penetrating already. And then there was gamma radiation, neutral, uncharged, moving straight without being deflected and very, very penetrating. We also saw what that big role of precision instruments was in these early discoveries. We saw how the Curie method was developed and that in fact Pierre and Marie used in their initial characterization of the strength of radiation given off by different minerals. And then later on, we saw the rise of particle counters. While the Curie method was just giving you an overall aggregate measurement, if you will, of the overall activity of a source, Geiger and Rutherford built the first particle counter. It has a gaseous vessel, and if any time a particle enters, an alpha particle enters, the instrument would give off a click. For the first time, you could really see individual such particles as opposed to just a long-term average. And then very quickly, and that to me is the most astounding fact, radioactivity went from being the subject of science and study of its own to being a tool for other branches of discovery. In 1913, we saw the first of these big discoveries. In Manchester in the UK, Geiger, Marsden, and Rutherford witnessed how alpha particles were scattered off, even a very thin foil of gold, some of them even bouncing back the way they came from, which then Rutherford interpreted as meaning that the atom, in fact, has a very dense, very small, positively charged nucleus. A few years after that, Marsden and Rutherford continued to push on. They studied the structure of the nucleus itself, and they found that it is not just a point-like object that doesn't have anything inside it. In fact, it's built up with even smaller things that they called H particles, and today we call protons, which show up in, that's why they gave it the name it had, came from hydrogen atoms. And then more discoveries started coming in. 1932, after World War I, James Chadwick noticed that if you had alpha particles impinging on a foil of beryllium, thin, soft metal like aluminum, you get a new kind of radiation, even more penetrating than the gamma rays, and that meant it also had to be electrically neutral. Now, Chadwick correctly attributed this radiation from coming also from within the nucleus of the atom, and so that meant, in fact, there is more than just the proton, the H particle in that nucleus, there is also something new, that yellow neutron. And that neutron is going to be sort of the star of the show today, and the name of the neutron and its history is strongly associated with this name. Of this person, Enrico Fermi. Now, Fermi was born in Rome. He was the son of a railroad engineer, and it was when he was picking up his father from his office one evening that he got to talk with a colleague of his father's, another engineer at that railway company, when he was a young kid, in fact. And that engineer, that colleague of his father's, he recognized Fermi's very quick sense of grasping the gist of things, and the two talked, and so he gave the young Fermi a book on geometry. Now that was all that Fermi really needed. He sort of plunged headfirst into reading that book. He read it from beginning to end. He solved all the exercises in the back of the book and then handed it back to that engineer who gave it to him. Now, when the time came to study and go to university, Fermi wanted to go to the best university in Italy at that time, that was in Pisa. Now, his parents were a bit reluctant to see him go. He would have to leave Rome, of course, and move to Pisa, because Fermi's brother, in fact, had just passed away, and his parents didn't really want to see another son sort of leave the house. But they realized how important at that time and how invested Fermi already was in the study of physics. And so to Pisa he went. And after Pisa, after finishing his studies, he moved to Germany, to Göttingen, which was at that time the center of the world of theoretical physics, where unfortunately he wasn't very happy. He didn't really feel welcome, and the luminaries that he wanted to work with, they didn't really see him as a welcome guest, if you will, at their institute. So he moved on to Leiden, that we also had visited in the past, and then he came back to Italy, to Florence. And by that time he was already a very well-known, well-decorated physicist. Now, his attitude of physics was a very particular one, and it's sort of perfectly hit on its nail by this quote here. I can calculate anything in physics within a factor 2 on a few sheets, but to get it fully right may well take a physicist a year, but I'm not interested in that. So he was always, from a very young age, curious about the very gist, the crucial thing at the core that made something work. And once he had understood that, obviously there were many details left to understand, but he was comfortable leaving those to somebody else, and he would move on to doing something else. And so when we meet Fermi on our quest of the neutron, he was already back in Rome. He moved from Florence back to Rome, where he was now head of a small research group. And they called themselves the Via Panisperna Boys, because this is the road, Panisperna Road, where their institute was located. So here's a photograph of some members of that group. To the very right there is Enrico Fermi. And the group was very, very close socially. They were not just colleagues who worked together, but they really enjoyed each other's presence, and so they had nicknames for each other. Now Fermi, having that aura of being infallible at physics, he was obviously the Pope. Now the right-hand side of the Pope, and also the right-hand man of the real Pope and the right-hand man of Fermi in that institute, was Franco Rasetti. And he was the Cardinal Vicar. Cardinal Vicar being the Bishop of Rome, in the Vatican a few miles away. Then there was Edoardo Amaldi, who was later to have a very big impact in particle physics, and he was a PhD student at the time. He was relatively younger than all the rest, and he was aptly named the young boy. Now, there's one person who is above the Pope, and that was Orso Corbino, who was the director of the institute, and his nickname was God Almighty. What else could it be? So this is the environment in which they were living and working. And this was the year and the times when there was big news coming out of Paris. The big news came from these two people that we already met briefly last time, Frédéric Joliot and Irène Curie, Irène being the daughter of Marie Curie, herself a big scientist and later Nobel Prize winner. The two of them followed in the footsteps of Marie Curie and did experiments with radioactivity. So the year we're in is 1934, and what they had done is the following. Our latest experiments have shown a very striking fact. So what they did is they took a very strong polonium source. Remember polonium, that first element that her mother discovered, a very strong source of alpha rays, and they put an aluminum foil next to that polonium source, and they irradiate the aluminum foil. And then later they take the foil away and they put it next to a Geiger counter, okay, that instrument that counts individual alpha emissions. And what they found is that first of all, that aluminum foil became radioactive after sitting next to that source for a bit, and that furthermore, the emission of that radiation from the foil does not cease immediately when the source is removed, or when the foil is removed from the source. The foil instead remains radioactive, and the emission of radiation decays exponentially as for an ordinary radio element. Okay, so that means, here is their lab notebook, and you can see they wrote out the counts registered by their instrument every half a minute at first, and then every minute later on. And you can see how the counts go down slowly as a function of time. So when they had just removed the foil from the source, the foil was extremely radioactive, but very quickly the activity of that foil dwindled down, and then in fact it became very, very low at a later time. And they correctly recognized that as there being some new radioactive element living inside that foil that had not been there at first, but that had somehow been brought to life by being next to that polonium source. And so this is what they wrote up in their report. artificial production of a new kind of radio element, Frédéric Joliot, Irene Curie. And of course, Fermi in Rome and his team, they would read that report. And they would think about it. And so Fermi says, okay, it's clear what happens. Rutherford taught us that in most cases, when that alpha particle approaches a nucleus, it would just be deflected off and be scattered in a different direction, maybe even back the way it came from. But every so often, things are just right for that alpha particle to hit the nucleus. Okay, it's not deflected, and when it hits the nucleus of that aluminum atom, it will turn that aluminum nucleus into a nucleus of phosphorus. Okay, 2 places to the right in the periodic table. Now phosphorus, that isotope of phosphorus, is not stable, it would decay, and that decay is what gave them their new radioisotope that they measured. Now Fermi says that's fine, but for this to work, you see, you really had to have a super high intensity alpha source, because in fact most of the alpha particles don't do anything, they just get deflected away, and that's because Rutherford discovered that thing first, because it was so dominant and happened so often. But if you have a really, really strong source, you can still get a significant number of these cases, where the alpha particle makes it all the way through. But most of them, they don't reach the nucleus. Now, so Fermi starts thinking, because he doesn't have a very strong alpha source at his disposal, but he starts thinking about neutrons. So what if instead, having something that is positively charged, such as the alpha particles, what if we had neutrons that did not have any charge? They might have a much easier time sort of going through that outer shell of the atom and reaching the nucleus. Okay, the uncharged neutrons, they would not get deflected by that repulsive electric force of that nucleus. But on the other hand, it's not a free lunch, he says, because you still need to have a neutron source, and the neutron sources that were available at the time in the world, they were just a lot lower in intensity than the alpha sources. Okay, so you make your life a lot easier, because the neutron has an easier time getting to the core of the atom, but at the same time you make your life harder, because now you need to produce the neutrons, and that was in itself difficult. And in fact, he was not the only one having that idea. After the Curies published their report, it was common knowledge that this was an interesting study to do, and many people, including James Chadwick in Britain and Rutherford, also in Cambridge, they were also in the game. And all of these minds had their attention set on that problem. But Fermi decided to try anyways, and so they needed to build a neutron source. Now, if you remember, what James Chadwick had done to produce his neutron source was to take some alpha emitter, okay, polonium in his case, and then just to put it next to a foil of beryllium, and then the neutrons would get converted, so the alpha particles would get converted by the beryllium into the neutrons that would come out the other end. So Fermi needed an alpha source. And it turns out that that building in which they had their offices, in fact, did have an alpha source. It was in the basement, but it belonged to a different entity in the university. It belonged to the Institute of Public Health, which was very reluctant to give up that alpha source and allow Fermi to use it for their experiments. So that was out of the question, but there was something else that they could do, because a decay product of radium, whenever a radium atom emits an alpha particle, it turns into radon. Now, radon is a gas, and it accumulates in the vessel in which you keep the source. And so the radium would itself be, if you will, a constant source of radon gas that could then be sort of siphoned off and used to do something else. And now the Institute of Public Health, having that radium as a source that would always constantly produce radon, was a lot more likely to give off some of the radon gas to Fermi and his colleagues than to really let their hands off that radium source. So they got some radon gas, which in itself is radioactive and a source of alpha particles, so they could use that. Now, how did they make a neutron source? They took a small glass vessel, they put beryllium powder inside, super finely ground beryllium, and then they filled that glass vessel with the radon gas. And now you have that same situation where the alpha particles that came from the radon, they're sort of very closely mixed with that beryllium, and so the same process happens. Beryllium converts the alphas into neutrons, and that little phial of glass that they had was their alpha source, was their neutron source. And so then they took the neutron source and they used it to irradiate all kinds of elements. And like the Curies had done before, they worked their way through all the different isotopes or different elements: silicon, aluminum, copper, tellurium, iodine, whichever materials they could get their hands on. And they recorded in each case how strong the effect of activation of sort of artificially produced radioisotopes would be in each case. And they wrote words in their report, very strong, rather small, strong, intense, whatever. And you can tell already by them not being very precise that this was a difficult measurement to do. And one of the things that made it so difficult was the fact that to irradiate that sample of material, you had to put it close to the neutron source, which was very intensely radioactive because it was the radon. But then to measure a small amount of activation, you had to put that sample that you just irradiated next to your detector. And that detector itself had to be in a space that does not contain a lot of radioactivity, because otherwise you would just get swamped by that, and you would not see that small amount of additional radioactivity that you had just produced. At the same time, you couldn't just afford a lot of time to leisurely carry the sample from one room to the other, because these isotopes that you might generate could be very short-lived. And so if you took a lot of time to really transport your transport your sample to your detector, they might have already decayed away and you wouldn't see anything. So what they did is they were living in the 3rd floor of that building there in Rome, in their Via Panisperna. They did the irradiation with their neutron source on one end of the corridor. They set up their counter on the far side of the corridor, as far away from that irradiation place as they could. And then they were literally sprinting down the corridor with sample in hand after each irradiation run. Now, Fermi was a very athletic person for his entire life, and he took pride in sort of always being in the front row of these kind of things. And he would be a very competitive person. He took pride in always being the fastest runner down the corridor. And we'll see that come back later. So this is what they did. This is what they had to do to pull off these measurements, but still, they weren't really precise. Right? And you can imagine, a scientist of the caliber of Fermi certainly wouldn't have been satisfied with writing vague terms, if rather small, very strong, and so forth. So what was going on? What was going on was, in fact, that they were having lots of troubles doing that experiment in a controlled way. And so what they tried to do is to decide to use silver as some sort of reference material. They would activate silver in a very standardized, reproducible way. They would measure the activation of silver, and then they would take another material that they wanted to activate, did it in exactly the same way, and then compared the two readings between silver and that other measurement, that other element that they irradiated. And then that would give them a way to compare, against silver, how much more or how much less radioactive their sample was. Now, it turns out that they wanted to use silver, but in fact, it was already very difficult to even do that reproducibly. So now I need to tell you a bit on how they pulled off their experiment. So they had their neutron source, and they had their target material, which in this case was silver. Now, their neutron source was this glass vial, and they drilled a hole, in fact, inside their target, into which they could then insert the source. Okay, that's already taking care of many of these sort of variables that you might consider in an experiment like this. If you just put the material and the source on a table next to each other, you need to make sure that the distance is always exactly the same and that there is nothing sort of around it or in between and so forth. Simply drilling a hole inside the material and inserting the neutron source there made sure that they could reliably and reproducibly position the source relative to their target. But it turns out that whether they did their experiments in a wooden table on the lab or on a marble table in the lab made a big difference. In fact, whatever they managed to do with that silver activation was a lot stronger if they used a table that's made of wood instead of a table that's made from marble. Okay, there was clearly something that was going on and that nobody understood. And so Fermi says, we were working very hard in the neutron-induced radioactivity, and the results we were getting made no sense. Okay, it was that wooden versus marble table story. One day, as I came to the laboratory, it occurred to me that I should examine the effect of placing a piece of lead before the incident neutrons. Because if Fermi thinks maybe what that source is producing is certainly neutrons, we've established that, but maybe it also emits other types of radiation that can have an effect on our probe, on our sample, and that, okay, if I put a lead sort of sleeve around it, I might be able to shield them and really just get the neutrons. So Fermi says, I took great pains to have the piece of lead precisely machined. Okay, he wants to make sure he's not missing anything, and in fact, he also points out that this is quite to the contrary of his normal style of working. Normally, he would just throw something together to see what it would do and how it would work. But in this case, he really took great pains to have it precisely machined and to have a lead sleeve that would snugly fit inside that hole that they bored in the silver. But then he says, I tried every excuse to postpone putting the piece of lead in its place. Okay, he has it ready, he has it machined, it's sitting there on his table, but something in him doesn't want to put it in the place that he had decided it should go. When finally, with some reluctance, I was going to put it in its place, I said to myself, no, I don't want this piece of lead here. What I want is a piece of paraffin. And that's what he does. He puts the lead away and he takes a block of paraffin, which is effectively candle wax, and he puts it next to the silver. And lo and behold, suddenly the activation becomes a lot stronger. Even if they do it on a marble table, it became stronger by a lot than what the wooden table had given them. So instead of doing the lead, he used paraffin, and clearly something was happening. And Fermi figured out what was happening over lunch that day, in fact. So what was happening is the following. Whenever you had a fast neutron coming from that source, it would hit some of the atoms inside that paraffin. Now, candle wax is mostly hydrogen, and so these atoms that it would encounter inside the candle wax is mostly hydrogen atoms that are very, very light. And so a neutron can easily sort of scatter on a hydrogen atom, which is effectively the same mass as the neutron, and lose a lot of energy in its process, because it would give a shove to these hydrogen atoms and then change its direction, and the same would happen in a different place, and so on and so forth. So the fast neutron from the source would sort of go back and forth through that candle box, at the end of which it would be a lot slower. Now, this is what happened. The fast neutron coming from their sources would sort of reach the paraffin, then zigzag around the paraffin, and maybe some of them would even be reflected back into the silver, but at a much, much lower velocity. And it turns out that these slower neutrons have a much, much easier time getting captured and staying inside the nucleus of the silver. It's also somehow sort of intuitive. If you imagine a superfast neutron zipping past that silver nucleus, the nucleus doesn't really have time to grab it and sort of integrate it into the nucleus. If it's a lot slower, that happens much more frequently. And that's why the activation of that silver, once the additional neutron is in, was a lot more frequent. And in fact, you then get a silver nucleus with an additional neutron, which was unstable and decayed, and that's the activity that I could measure. And now it was also clear why that happened in wood, because wood contains water, and water contains hydrogen. So just the presence of that wooden tabletop was enough to already increase the effective activation of silver. And of course, if you do paraffin on purpose, you would just enhance that effect even more. Further investigations, that's again quoting from their report, further investigation showed that the activation could be enormously increased by surrounding the source and the activated substance with a large amount of water, which also has hydrogen, or paraffin wax. And so they had discovered slow neutrons and a process of turning fast neutrons into slow ones, and they took out the United States patent on it. Process for the production of radioactive substances, and all the names on that patent are the names of that group of scientists that we just saw before. And the apparatus that they patented was, in fact, the exact apparatus that they had just used in the lab. They had big blocks of paraffin that sort of enshrouded everything. They had a small hole inside into which they could place their long, slender glass tube that contains their neutron source. And then in this cavity inside, they can put whichever material they wanted to activate. And so the neutrons from the source would sort of wiggle around in the paraffin and then reach that target material, and by which time they would be very slow, and they would be easily absorbed by the nucleus inside and activate that material. And so it was just a question of time before they started activating uranium with slow neutrons. Now that they had gotten a much better handle on how to design and conduct these experiments, and they knew much better of what was important, namely the presence of hydrogen around their environment, they, of course, could do it on purpose. They put their materials inside their paraffin shroud that we just saw, and they repeated their measurements. And it was natural that they would also try uranium. Now, what they found after they irradiated uranium was a very distinct new element with a half-life of 13 minutes. Okay, they irradiated the uranium, they took it out, put it next to the counter, and they watched the activity decay with a half-life of 13 minutes. And obviously, they were wondering, which new element inside that activated uranium is now responsible for that 13-minute decay. And they did the same thing that the Curies did. They tried to chemically isolate that new substance, okay, by taking that uranium probe and then processing it through various chemical extractions, targeted to different elements that they could extract. And so they tried, maybe it's uranium itself, but an unstable version thereof at 92 protons and maybe one additional neutron. But their tests came back negative. That was not contained. That was not the source of that 13-minute half-life. So they go and take the next lightest element, palladium, 91 protons, also not the case. Thorium with 90, also not the case. Actinium, 89, also not the case. Radium, 88, also not the case. And they go all the way down and try lighter and lighter elements until they reach lead with 82 protons, but lead was also not it. And then they stop, because they could not imagine anything that could possibly make this element be lighter than lead. It's nothing in between 92 and 82. And so they say, maybe it's something that's heavier than 92. Maybe there is indeed a new element that we've just created inside the uranium that decays at a 13-minute half-life that contains more than 92 protons. Okay, and that process is very sensible. You have that slow neutron hitting that very large uranium nucleus, adding one neutron to that nucleus produces a new heavy element, which then decays at 13-minute half-life. And so they write this new paper, Possible Production of Elements of Atomic Number Higher than 92, and they publish it on June 16, 1934. Now, these were the times when a lot was happening in Europe, politically, one of which was that Benito Mussolini, the fascists, they take power in Italy. Now, Fermi's wife was Jewish, and as Hitler rose in Germany, it became more and more untenable for them to stay in Italy, because Hitler was putting a lot of pressure on Mussolini on racial questions and obviously the Jews. So they had to leave. That was in 1938 when, conveniently, Fermi was awarded the Nobel Prize for physics in 1938 on his work on neutron-induced radioactivity that we had just discussed. And so they had been planning to already leave Italy before the announcement of the prize came through. But now that he had won the prize, they needed to attend that award ceremony in Stockholm in December of 1938, and that's what they did. But instead of going back to Italy, they then boarded a ship that took them to New York, where Fermi and his wife and their 2 children arrived on January the 2nd, the year after, 1939. Now, Fermi had made arrangements to be given a small position, an office effectively, at Columbia University in Upper Manhattan, and at Pupin Hall, in fact, where the physics department was residing, and he took up an office there. And then everything started to happen simultaneously. Now, he arrived there on January the 2nd. On January the 6th of that year, news broke that the uranium nucleus had been split in Berlin. Had been split by this group of 3 German chemists and physicists, Otto Hahn, Lise Meitner, and Fritz Strassmann, and they published a report on that January the 6th, 1939, in a German journal, okay, about how they split the uranium nucleus. Now, what had happened in Berlin was effectively the exact same thing that Fermi did in Rome 4 years before that. They had a source of neutrons. Theirs worked a bit differently, but it doesn't really matter. They sent it through paraffin to slow them down and de-irradiated uranium. And then they took the uranium out and they subjected it to a chemical analysis, just like Fermi and his group had done. And so what they found is they did a very precise mapping of all of the decays that they could pick out and all of the elements that were responsible for these decays. So they put everything in quote marks because at this point they're not certain as of the sort of chemical identity of these elements. So there's 4 different kinds of, quote, radium that they found that then decay into 4 different kinds of actinium, and then that's still unstable and decays into 4 different kinds of thorium. Now note here that one of these, the second kind of radium, has exactly that 13 or 14-minute, in their case, half-life that Fermi was picking up on. Okay, so this was the same evidence that Fermi had, if you will. But then, the German group, they were effectively the world's leading radiochemists at that time. And the crux of the experiment, as you shall see, really lies in the chemistry that you do, not in the irradiation itself. And they say, as chemists, because of the way these elements behave, it would actually have to say that the new elements over here, they're not radium, they're actually barium. Okay? But then, if they say if our radium isotopes, in quotes, are not really radium, then the actinium isotopes that come from the decay of these radium, they're not actinium, but they're actually lanthanum. Now, and then they also have this wonderful sentence in their paper that says, okay, as chemists, we would have to believe that these are barium and lanthanum, but as physicists that we also are, we don't really believe it. Because barium and lanthanum, they're just so much lighter than uranium. And nobody could, at this point, really imagine a credible process that could take uranium with 92 protons into lanthanum, which has around 50 or 55 protons. It's effectively halving that nucleus. So what was going on? Now, today we know what was going on, which is, in fact, that the nucleus is a highly dynamic object. It's much more like a droplet of water instead of a billiard ball, if you will. So if you imagine that big, sort of over-fat droplet of water that is the uranium nucleus, and you add an additional small droplet of water, the entire thing can start to wobble and sort of move around, and the uranium nucleus starts to wobble and move around, and sometimes it can happen that, in fact, it splits in 2 halves, one of which is then roughly half the weight of uranium, and that's barium at 56 protons that they couldn't quite make themselves discovering, if you will. And the other side was technetium, which then managed to add these two things up to give the uranium. Now, the experiment that they did was exactly the same to the one that Fermi was doing. They did the exact same iteration procedure, they found the same elements with the same half-life, they did the same analysis. They were a bit more thorough because Fermi stopped at 82. Had Fermi continued and his team, the testing for lighter and lighter and lighter atoms, they would have no doubt discovered barium, and they would have no doubt discovered the fission of uranium 4 years earlier than what it was eventually discovered. So you can imagine how Fermi must have reacted when he got the news. Yet not only did his discovery of new transuranic elements just vanish and disappear, it was not true. He had just, in December, given a Nobel lecture at the prize ceremony talking about his research and about the possible discovery of transuranic elements. Now imagine how embarrassed he must have been, but his reaction was, okay, I really want to go and now do the experiment again. I want to see it for myself. And I want to see it in a way that is unambiguous and that doesn't make me rely on chemistry anywhere down that line. And so he recruits a grad student, Herb Anderson, who was at Columbia at the time as well. And the two of them, they go and they build an experiment. Now, the experiment that they did was, broadly speaking, very, very similar to what the Curies had done. They took a parallel plate ionization chamber, such as what the Curies used in Paris, two parallel metal plates, but they covered the insides of these plates with uranium. Okay, and then they hooked that chamber up to their measurement equipment. And then they built a neutron source, which they did in exactly the same way that Fermi was comfortable doing, because he did it in Rome many times. And they put the neutron source inside, in between these two plates. And then when they watched what the counter would give them, what the instrument would give them, is they would see the following. That happened in February, mid-February of 39. You can see it didn't really take a long time to assemble and conduct this experiment. It was sort of state-of-the-art equipment that was commonly lying around in the lab at this time. But what they see is the following. They see a large number of small pulses, down here, which are coming from the uranium. The uranium decays, it produces alpha particles, and the alpha particles, this is what the Curies used that chamber for, obviously gives some small signals. But then you can also see these much, much larger signals there, these larger peaks, and they only occur when they put the neutron source inside, but they disappear the moment they take it out. So only when the uranium is exposed to bombardment of the neutrons, something a lot more explosive is happening inside that's a lot larger than what the alpha decays do, and that's the uranium nucleus blowing apart. So here was the unequivocal proof of the fission of uranium in a way that doesn't rely on chemistry. You could literally see it on their scope. And so this was the time when a question became very, very important. And that is, did anything else happen when the uranium nucleus is flying apart? So now we know that we get barium and lanthanum and all kinds of other elements. But do you potentially also get something else? Do you potentially get additional neutrons out the other end of that explosion? And if so, how many neutrons did you get? That's a very important question indeed, because you can imagine if on average you get less than one neutron, then no matter what you do, this one neutron can go on and do whatever. If it's less than one on average, the reaction will eventually peter out and stop. But if it's more than one neutron on average, then if under the right conditions, you could set up things such that these more than one neutrons would find another uranium nucleus that they would then cause to fission. And so potentially, there is this possibility of the reaction going on indefinitely. Now, the wonderful thing about this question is that there is a sharp answer. The answer is given by the laws of nuclear physics. There is no ifs or buts. It's a sharp question with a sharp answer, and there's a sharp line in between these two possibilities. And everybody knew that, nature had to decide which end of the line, we're on, but the potential future that would ensue would look dramatically different depending on which side of the line we're on. And everybody was aware of the significance of that. And so the question was, how many neutrons? And it was a question that could be solved only by experiment, and so an experiment they built. And in this case, it was Fermi and another Hungarian refugee at Columbia at the time, Leo Szilard. So the two of them go together and they build the following apparatus. They take a large tank of water and they dissolve some salt in the water. The idea being that the salt in the water, if there is some neutrons present, the salt would get activated, just like the material samples from before, and then I could simply take a scoop out of the water and analyze it. I put it next to a Geiger counter, and then the activity of that water would effectively tell them, it would depend on how many neutrons the water had seen. If there were many neutrons, the salt would get more activated, the sample of water would become more radioactive. And so they needed a neutron source, and they put one at the very center here. Again, it's made of radium and beryllium and such, in a very common way, and the neutrons would all come out of that source in the very center of the apparatus. And around that neutron source, in those cylinders that you can see, they put uranium. And then they measured, with the uranium present, or without the uranium present, how much more neutrons they could see. Okay, that would tell them what the uranium did to the neutrons from the source. Did it multiply them, or did it sort of diminish them? And what they found is that, in fact, the activity of the water with the uranium present was about 10% higher than if the uranium was not inside that device. Okay, so that meant something very profound. It is that uranium adds more neutrons to the pool than it takes out. I mean, you can imagine if you put some uranium inside, it will displace some of the water that had been there before. And if uranium was sort of eagerly capturing neutrons, you might in fact have less neutrons with the uranium in than without the uranium. But in this case, you ended up with more neutrons, which meant the uranium contributed more than what it took out. And they managed to convert that measurement, and they said it corresponds to about an average emission of 1.2 neutrons per neutron absorbed by uranium. Okay, 1.2 is greater than 1. And so if you will, the die had been cast there and then, and we are on the right-hand side of that line. This is the world that we live in. And they published this. 1939, August, still that marvelous year of 1939, neutron production and absorption in uranium. It was Fermi, Szilard, and there was also Herb Anderson, that grad student. Now there's also another fun story about this experiment, which is that Fermi and Szilard, in fact, had very opposing work habits, and they didn't end up collaborating again, because Fermi at least didn't quite enjoy the experience. Fermi, as we saw, was always taking great pride in being in the front row of the experiment, take on whatever task fell to his lot, being sprinting down a corridor doing other things. He was not sort of shying away from hard work. Leo Szilard, instead, was more the kind of person who hired an assistant to do sort of the dirty work for him, and then sort of he would sit back and sort of watch or sit on his desk, do other things. And Fermi didn't appreciate that. Okay, he was of the opinion that whoever was on the team had to do what it takes to make the experiment succeed. Now, Szilard, on the other hand, had other talents. He was extremely good at scrounging materials. Okay, he could pull, the threads that he had, and that's what he did to get the uranium that they had. They needed 400 pounds of uranium, which Szilard managed to get on loan from the El Dorado Radium Company that owned large uranium deposits in Canada. Okay, so through different back rooms, he managed to get his hands on a large amount of uranium, 400 pounds, which is what it took. Now the question was, now that we know that we're above 1, it means in principle we could have a self-sustaining chain reaction, but if something is easy in principle, it doesn't mean it's easy in practice. Okay, so how do you make it work in practice, or can you make it work in practice? Now the problem is that there are 1.2 neutrons, which was later corrected upwards to 1.5. It's larger than 1, but it's still quite tight. It doesn't really give you a lot of wiggle room. The moment you fall below 1, the reaction peters out. And you can see why this is a hard problem, because you start out with a slow neutron causing that fission that we saw. Then, if you get on average more than 1 fast neutron, that entire fast neutron would have to go through that slowing down procedure, that moderation procedure, in whatever material that they put. It would go through multiple collisions to be slowed down, and then, once being slowed down, it would have to encounter the next uranium nucleus and then cause another fission. And you couldn't afford to lose, through that entire chain, you couldn't afford to lose more than half a neutron on average. Because if you did, it would not work. It would not be a self-sustaining chain reaction. So it was actually quite difficult. You had to slow down the neutrons, but you couldn't afford to lose them. Okay, it was now an engineering problem rather than a fundamental science problem. And so the question became, which material to use for that job of slowing down the neutrons? Which moderator, as they called it, should they use? And now, as always in engineering, there is a trade-off between multiple things that cannot possibly be true at the same time, but that you would want to be true at the same time. One of which is that the moderator, as we saw, hydrogen was ideal. The atoms had to be light, because only if the atoms were light could the neutrons very effectively lose their energy and slow down. You also wanted to have these light atoms be very densely packed, okay, so that the neutron has many chances of encountering a light atom and colliding with it. And you also want these light atoms that are densely packed to not absorb any neutrons and take them out of the pool, because that was dangerous. That would immediately bring you down below that magic line at 1. And so they just went through all the elements that they could consider, starting from the light ones and working their way up to the heavy ones. The 2 lightest ones, hydrogen and helium, they ruled out because they were gases. And gases did not really have densely packed atoms inside them. Then there were lithium and beryllium, and then there was boron, and then there was carbon. So these 2, gaseous, you cannot really have hydrogen be very dense or helium be very dense. They're light atoms, but if you only have a tiny number of them in your volume, that's no good. So these ones are ruled out. Lithium and beryllium, in fact, they are metals, so you could imagine that they're easy to work with, but in fact, they're very chemically dangerous. They're very reactive, and they have a danger of blowing up, and so that's also not what you want. Now, boron, in fact, they did consider, but there were no easily available sources of boron at that time. The major deposits were in Turkey, which was on the other side of the Atlantic, and it was difficult in these days to really get reliable shipments of boron, so that was ruled out. And so they settled on carbon. Carbon, in the form of graphite, is very common. It's very easy to produce. It's relatively cheap. It's not dangerous. It's effectively what is in your pencil. So carbon it was. And so the next thing became a question of engineering. How do neutrons propagate through carbon? And they, again, solved that problem or asked that question with experiments. In the basement of Pupin Hall at Columbia, they started building test piles. Okay, they were effectively blocks of graphite stacked up on top of each other, and then they would have little slots opened into them, and into these slots they would insert long strips of metal, in that case rhodium foil, and the rhodium foil, once they put the neutron source in, the rhodium foil would get activated by the neutrons passing it, and then later on they could take it out and analyze it with their counters, and so reconstruct how many neutrons the foil had seen. Okay? And that would tell them how the neutrons from the source at the top of the pile would sort of go down and sort of collide, and how their trajectories would change as they went further down and down and down into the pile. And so again, it was Fermi who was in the front lines of carrying these samples down the corridor of Pupin Hall next to the counters. But what they found is a disaster, and that was in spring of 1940, because most of the neutrons didn't actually make it to the bottom end of the pile. Most of them, they stopped. They got absorbed somewhere in the graphite. It was disastrous because you had too many neutrons that were absorbed. And in fact, they traced it down to impurities in the graphite. It wasn't the graphite itself that was absorbing them. It was boron that was a byproduct of the production of graphite, which they didn't realize up until then. Boron is very, very absorptive of neutrons. It has a very high tendency to catch them and to take them out. And in the process, it would just ruin their experiment. So every carbon atom that the neutron would encounter would easily slow it down by a certain amount, deflect it in a different direction. But if there were sufficiently many boron nuclei inside that pile, this is where the trajectory would terminate. It would go no further. And so Leo Szilard, again, and his skills at getting materials handy were very important. He worked closely with the National Carbon Company in Cleveland, Ohio, to produce and secure the supplies of graphite that they needed. And he exchanged many letters with engineers at the graphite company, and they're quite amusing to read. So here's a letter that Szilard sends in February 1941, so the year they were doing these experiments at Columbia, to the National Carbon Company in Cleveland, Ohio. So here's what he says. This is just after that presence of boron inside their graphite had emerged. We regret to hear that you are not in a position to supply graphite bricks free of boron to meet certain specifications of ours. You can see he's sort of dancing around that line of secrecy that was already enshrouding the project at the time. He spoke of certain specifications. He wasn't really clear what that meant. But they would still be very much interested to learn the boron content of the best graphite which you're able to supply. Because they might still be able to make certain uses of the graphite, which again, he was not very specific about. And so this was a long back and forth between the manufacturer of the graphite and the teams putting it to use. Okay, the one providing feedback to the other and then going back and forth to see if the manufacturing process of the graphite could be improved. And in fact, it could be improved because they managed to make a lot of progress. And many more test piles started going up in the basement of Pupin Hall at Columbia. Now we're in September of that year, and their piles have grown, 8 feet by 8 feet by 11 feet. And now they have already included some uranium inside that graphite. It's no longer just graphite to study how the neutrons would go through. It's now also containing uranium fuel. Okay, in a regular, if you will, grid, they put uranium fuel pellets in a regular grid. The idea being that if there is a fission reaction in one of the pellets, the neutron would sort of go out. It would go through the graphite, and by the time it reaches another fuel pellet, would already have been slowed down by that intervening graphite and then cause fission in the next pellet. And then I put a neutron source at the bottom again to start everything up, and then they used their foils again to do the measurements. And so it was a very much a build and test and iterate kind of approach rather than doing all the calculations up front, which at that time they didn't really have a lot of knowledge how to do them anyways. So it was all experimental. But still, with the much improved graphite and with the much larger pile and the sort of efficient arrangement of the fuel inside, they still fell about 13% short of achieving a self-sustaining chain reaction. Okay, they pulled all the tricks that they could at this time, but they still didn't have. They still had too many losses of neutrons down the ends of the pile and elsewhere that made them fall short of that magic line at 1 that they wanted to cross. Now it's December 1949, and now things change again, because this is when the attack on Pearl Harbor happened, and this is when the United States was now formally at war with Japan and with Germany. So the context in which they were conducting their work is now very different. Where previously this was a sort of rather loosely managed effort at different universities, Columbia, a bit in Chicago, in Princeton, now suddenly there was a lot more urgency, and suddenly there was a lot more money on the table. The government had provided some funding to secure graphite and so forth, but now we're talking about very different scales. So there were committees put in charge to organize the effort and ramp them up to a larger scale, and one of the people in charge was nobody else than Arthur Compton. And he decided to bring together all of the university groups that up to now had been working independently of each other along the East Coast, and there were some people from Berkeley, and decided to put them all together. And that place where he would bring everybody together would be Chicago. So to Chicago they moved, and they established what was called the Metallurgical Laboratory, which partly was a cover name for what they were actually doing, but partly it was also true, because one of their byproducts was to study, if you will, eventually, metallic plutonium, which by now, at this time, was still science fiction. But the administrative staff would take up their quarters in Eckert Hall at the university here, which today is where the mathematicians are housed. Now the experimentalists needed a place to put their test piles up, and that place was Stagg Field, which, this is what it looked like around 1900, sort of looking down south, Ellis, so here's 57th Street. This is what was then the football court of the university, which, around the time that everybody moved to Chicago in the 1930s, had been renamed to Stagg Field, and these flimsy wooden construction was replaced by a proper, stone west stand. This is what they called it. Now, in the 1930s, the president of the university, Robert Hutchins, he called football an infernal nuisance that would in fact just distract from academics. So he shut down the football team, and now suddenly there was nobody using this area anymore. And so this is what it looked like in the 1930s. It fell into disuse and disrepair. And so there was a lot of space available for the scientists to use. And so they moved into the squash courts that were now not used anymore, and this is where they put up more test piles. They were continuing the work they started at Columbia underneath Stagg Field. And you can see, they built around 16 or so of these test piles in much the same way they had learned at Columbia. But it was clear to them, and it was already clear, in fact, by the time they left Columbia, that they had to have additional improvements if they wanted to cross that line. Just continuing as they were used to wouldn't do it. And so one of the problems of the Columbia piles was that they were easy to build. They were rectangular. And that meant there was a relatively large surface of the pile through which the neutrons could get lost. And any neutron that's lost would put down that average and would make you fall below that magic line at 1, and you were dead. Now, in principle, the perfect shape to build a pile in is a sphere, because a sphere has a relatively small surface area for the volume of graphite and fuel that it contains. So they wanted to approximate a perfect sphere with their blocks of graphite, and obviously it had to be imperfect, but they wanted to be as close to a sphere as they could get it. That was one improvement. The other improvement was to do with the instrumentation. If they were to build a pile for the explicit purpose of taking a step to the other side of that magic line at 1, they had to know what was going on. And up to now, if you remember, these metal foils inserted into the pile, then taken out and being carried to the counters, would only allow them to reconstruct after the fact what had emerged, what had happened inside that pile. But if you're about to drive your pile, to beyond criticality, to make it self-sustaining, you want to know sort of live what you're at and what's going on. And that was the project of Leona Woods, who had just finished her PhD, in fact, at Chicago by the time she joined the project. And she was working very closely with Herbert Anderson, that graduate student at Columbia that Fermi picked up and then brought with him to Chicago. And what they did was to turn, if you will, the nuisance of boron into a virtue. Because by now everybody knew that boron had a high tendency to absorb the neutron. It was terrible if it happened inside the graphite. But if you put a gas that contains boron in the place you wanted to measure the neutrons, that boron would capture all the neutrons that came its way, would turn into lithium, and in the process of turning into lithium, would also emit an alpha particle. And our alpha particles, people knew very well how to measure and how to detect. Even Rutherford and the Curies knew how to measure alpha particles. So that's what they did. They built a gas chamber, much along the lines of what Geiger and Rutherford had done in Manchester, but they didn't fill it with air, but they filled it with a gas that contains boron, and a convenient gas was boron trifluoride, BF3. And that chamber they would embed inside the pile, at the core of the pile, where they wanted to measure the rate of neutrons, and then they would run a long shielded cable over several hundreds of feet to where they could safely monitor the level of neutrons. This is where they would put their galvanometer, their measurement for current, and they would look at it and they would read out and they would see exactly what happened inside the pile 300 feet away. So then came the question of where to build that first pile. And Arthur Compton, who was in charge of leading the Chicago effort, the Met Lab, he decided to put it safely outside the bounds of the city then, near the Argonne Forest Preserve. This is what it was called back then. In fact, they wanted to put it to what they called Site A, which today is very close to sort of Redgate Woods, and then very close to the current location of the Argonne National Lab. Now, unfortunately, the workers that were putting up the buildings there, they were on strike, and they were way behind schedule. And so it was just not ready by the time Arthur Compton's very ambitious schedule demanded the building to be ready for them to move the pile in. And so the question became, should we rather move ahead and build it where we had just done all of our current experiments and everybody is familiar with the facility? Should we build that pile at Stack Field? And then this is when Arthur Compton needs to make an executive decision, because he says, as a responsible officer of the university, according to every rule of organizational protocol, I should have taken the matter to my superior, the president in his case of the university, but that would have been unfair, he says. Based on considerations of the university's welfare, the only answer the president could have given would have been no. There is no way that you're going to put this pile right next to where the students are, right into the heart of the university campus. And his answer would have been wrong. He says, so I assume the responsibility myself. He says he doesn't want to put the president into a situation where he has no way but to say no. So he just doesn't tell him and goes ahead. And so this is where what was later known as Chicago Pile 1 was indeed built, underneath the west stands at Stack Field, and it involved a lot of manual work. A lot of graphite had to be cut, a lot of wood, timber had to be cut just right, as you'll see, for the support structure that would hold up that graphite. And Arthur Compton was very keen on making sure that the morale of the team was high, the spirits were high, and so he encouraged everybody to participate and take shifts in cutting the graphite and carrying the heavy chunks and put them onto the pile and stack them and so forth. And in fact, many members of the team would do that, except Leo Szilard. Again, he would wiggle out of his duties and he would go off. And so this is how Chicago Pile 1 was built. Layer by layer, starting at the very bottom. Remember, they want to approximate a sphere, so the bottom had to be very, very narrow. They laid down the graphite bricks. And they put, as they were layering the graphite, they started building that support structure around it. And by the time they got to sort of the mid layers of the pile, the diameter had grown to a much, much larger extent. And then it narrows down again towards the top. And you can see again that there are these holes inside the graphite, which is where they put the uranium fuel pellets, in much the same way they had done prior to that at Columbia with their rectangular test piles. And they knew that they had to get it right, because at this point, the mechanisms behind these processes were very well understood, and people could predict that they should, in fact, be able to approach a self-sustaining chain reaction this time, but they wanted to make sure that they stayed in control all the way. And so every night, after they closed up shop for the day, they were doing measurements. After another layer of graphite had been put in place, they were measuring how close to that magic line of getting a self-sustaining chain reaction they had come. Okay, that magic line of having a self-sustaining chain reaction is at the bottom of that graph here. And you can see with every layer of graphite, they were sort of carefully inching down towards that line. And then around here, at 56 layers of graphite, this is where they had predicted, and then in fact measured, the critical point to be. But they knew exactly what they were doing because they could see it coming. It's not that, okay, it hit them by surprise. They knew exactly what they were up against. The second element was that they needed some means of controlling the activity of the reactor, of that chain reaction, as they were conducting the experiment. And so again, they used this wonderful ability of certain materials to absorb neutrons and take them out of the pool and prevent them to fission additional uranium atoms. And so they built long control rods or safety rods into their design, which were long brass rods that would slide into the pile horizontally. And the brass would be covered on one end with cadmium, which is a metal, so you could nicely sort of apply it on top of other metals, such as brass. But cadmium had much the same effect as boron. It would absorb the neutrons. And so this particular rod here was called the zip rod because it was hooked up to an automatic safety switch. There's some electromagnets in here, and it would be held in place with sort of a simple hook that would release if the radiation levels got too high, and then a weight on the other end would slide the rod in, even if there's a power cut or anything else happened. So this was an automated system that would make sure that the reactor was shut down in case something went wrong. Now on December 1st, 1942, they had built the pile to one layer beyond criticality, 57 in total. And on December 2nd, they were ready to start it up for the first time. And here's what it looked like. Down here is the timber support structure that holds all of that graphite in place. Remember, it's approximating a sphere, so it's much narrower at the bottom than it is up here. Then, in fact, they had envisioned another system, which they never had to use in the end. They made sure that they could, if the need arises, enshroud everything, the entire pile, in a fabric tent, a sort of airtight balloon fabric, such that if it had emerged, that they were sitting right at the edge of criticality, but they couldn't quite get across it, because the moisture in the air might also take out some of the neutrons, a very subtle effect, but it was true nonetheless, and they knew it. In case that prevented them from successfully operating, they would simply have flooded, they would have closed up that balloon tent, and they would have flooded the entire room with helium. That would have dispersed the moisture in the air, and that might have made them sort of come out on the other end of that line. In fact, they didn't need to use it because it was working as designed. But that's why the presence of that balloon tent also meant that the control rods and safety rods that were moving in and out, they had to be also enshrouded with an airtight housing to make sure that the helium didn't escape. And these are what these three sort of lines are that go into the core. And then everybody was up here on the balcony. All the leadership was present. There was Fermi, and there was Arthur Compton, and there was everybody else. And then down here, they had another control rod, this one manually operated. You could slide it in and out by hand. It also had boron on it. And they had George Weil positioned there, and he had his hand on that control rod, and he would listen out to the commands he would get from up on the balcony. And then up here, as a last-ditch effort, they had three people, Lichtenberg, Nair, and Graves. They called themselves the Liquid Control Squad, in case these control rods or safety rods, for some reason, couldn't be inserted automatically or manually because something went terribly wrong. They were ready with buckets full of cadmium and water that they could simply pour into the graphite from the top. The cadmium water would rain down inside the pile and then simply just stop it. Of course, it would also make everything unusable because then you had to disassemble everything and get the cadmium out before you could operate it again. So this was really a last-ditch, almost destructive way of shutting down the reactor. And so this is what happened on that day of December 2nd, 1942. Here is their chart of the neutron intensity as they were conducting their experiment. And Fermi is in control. Fermi is up on the balcony, and he oversees, and he gives the commands. And he has his slide rule at hand that he always uses to cross-check and make sure that he knows what's going on. So Fermi commands zip out. Okay, he refers to that zip rod that we had just seen, the one with the weight on the other end. The safety mechanism, people put it out. And then he calls out to George Weil, who has his hand on the manual rod. He says, pull it to 13 feet, George. And George pulls it to 13 feet, and you can see the neutron count rising. Starts up to rise, but then eventually it starts to remain constant. And I have these little comments written by hand after the fact on that paper tape to see what happened. And in fact, this here is exactly what Fermi says, control rod and zip rod out. Then they remove removal of cadmium number 2, this is what it says here. Another one of those cadmium rods go up, and again the neutron counts go up, but then they start flattening out again. And Fermi knows that things are flattening out because he has the slide rule and he has looking ahead of what's going to happen. He says, this is not it. The trace will go to this point, and he points at the tape. It will go to this point and then level off. Okay, Fermi knows how the pile behaves. He had seen it rise. He had built it himself. He knew how it would behave. And so he was very confident in making these assertions as the experiment went live. So here's 3 p.m., and then I pull out another rod, okay, the third one. And then the record gets a bit jangled up because they start approaching the top end of that paper tape, and so they have to switch the instrument to a different sensitivity range, or else they would run off the paper at the top. And this is why the line is sort of wildly jiggling up and down here. But then Fermi calls out, this is sort of, 3:30 or whatever, pull it out another foot, he calls out to George. And George pulls it out another foot, and the count starts rising again. But this time, you can see it looks different. And Fermi says, this is going to do it. And people watch, and he says, now it will become self-sustaining. The trace will climb and continue to climb, and it will not level off. And you can see it from the graph. At the very beginning, Fermi could see it, where previously it was very fast at the beginning, and then went slow and slow and slower. By pulling it out another foot, George Weil had put them on the other line. On the other side of that line, they were now having more than 1 neutron on average, and each uranium core that would fission would on average give them more than 1 in the next generation. And so the line would bend upwards, and it would continue to grow, and it would never stop. Of course, at some point, Fermi was convinced, everybody was convinced, and they said, okay, zip rod in, then most the safety rod in, and the reactor shuts down. And then they have an impromptu celebration, because one of the Hungarian guys, Eugene Wigner, had brought a bottle of Italian red wine, and he was hiding it behind his back all this time. And then he handed it to Fermi. And everybody signed their names. Everybody present signed their names on the bottle. And obviously nobody thought about setting up a proper celebration, so they didn't have wine glasses. They used paper cups, and everybody would have their sip of wine. And then they would turn off the lights, take the cadmium as far away from the reactor, which now was working, as far away from the reactor as they could to make sure that no accidents happened. And then they went out into the winter night, and they closed the doors behind them. And now is the time when we also need to step back and look back a bit. Because 8 weeks ago, we asked ourselves the question, in this world that we have with electricity and light and radio and mobile phones and elevators, how did we manage to get all of those things? And so now we have made it from Millennium Park out onto Ellis, and this is what that street corner looks like today. So we have arrived. And now that we know how we have sort of come here, and that was the story I wanted to tell you, now that we've heard the story, what is the answer? What did it really take us to get here? But one thing, of course, is curiosity. Think about the old Italians. Giovanni Sagredo, once he had built his thermometer and he tried to measure all of the marvelous things that he could, he did that because he was curious. Or think about Stephen Gray, who in his retirement got himself a large glass tube to see if he could make any further discoveries with it. He was driven by curiosity. Or think about Count Rumford, who already had so many things on his plate, designing uniforms, planting trees in Munich, being involved in the military, and still he did what he could to go after the true nature of heat, because he decided it was a question that is worth knowing the answer to. Another thing that it took is precise instruments. Think about Joseph Black. and his invention or discovery of this concept of specific heat. He could only pull that off because he had at his disposal very precise thermometers. Or think about Michael Faraday. He discovered induction by being able to measure very, very small amounts of current with his very precise galvanometer. Had he not had this precise instrument, he might have easily dismissed the evidence that he got. Or think about the Curies. Their discovery of polonium and radium was primarily because they were able to measure very precisely small amounts of radioactivity using their electrometer. It also took hard work. Think back to Charles Dufay, who set out to really systematically map out all the different materials and the kinds of electricity they would produce if you rub them against each other. And he discovered that there's two kinds of electricity. Or think about Mr. Newcomen, who built his atmospheric engine, and it took him 10 consecutive years of hard work to really go through his design. Or think about the Curies. Their extraction of radium really involved processing in an arduous and laborious way tons of pitchblende. And they would be exhausted each and every day. But then, what also was very important is in some sense the past lending a hand to the scientists of the present. Think about Faraday's discovery, or think about Heinrich Hertz's observation of electromagnetic waves that we had seen, or even about Rutherford's identification of alpha and beta radiation. All of those experiments relied on having an easily available constant source of electricity. And these experiments could not have been possible without the invention of the battery by Alessandro Volta. And in fact, all of these experiments used a battery in one form or another. Or think about Heinrich Hertz again. He got set on his track that would lead him to discover electromagnetic waves by finding and playing with a set of induction coils in his laboratory storage. Now, to get to that point where induction coils were presently found at universities, Michael Faraday first had to have a look at what loops of current did to magnetic fields. He would then play the ball to Joseph Henry, who would build more and more powerful electric magnets, and then that would eventually lead Michael Faraday again to discover induction. And only because of that did induction coils become sufficiently present that Heinrich Hertz could just run into one of them at the university he was at. Or even think about so-called serendipitous discoveries, such as the one by Henri Becquerel, who put his uranium salt on a photographic plate to discover natural radioactivity. He could not have made that so-called serendipitous discovery had not the Lumiere brothers and many others pioneered the science of photography before him. The very fact that he could simply buy and have readily available photographic film is really the result of a long chain of events that we didn't even have time to talk about. So what it took us to really get here is also that big dialogue between science that discovers new phenomena, and then of engineering that takes those phenomena and makes them useful and usable as tools that then feeds back to the next generation of scientists. And this is how fundamental science, in fact, did have a very big say in making the world what it is like today. And that's the end of the story I wanted to tell you, and I thank you very much for coming. So, questions? Yes?
Yeah, two questions and a comment. Was there any speculation found in the literature about the forces involved in the scattering of neutrons? Because there are no electrical forces involved. So, did anybody speculate on that?
So Fermi did, so the question is about neutrons. In fact, Fermi did know a lot about neutrons. That's also something that we didn't discuss. Because neutrons were known to not be stable. So neutrons were stable when they're inside an atom, but people already knew that neutrons would decay if they were not inside. And it was in fact Fermi who pioneered, Fermi was also a very good theoretical physicist, and Fermi pioneered the sort of understanding of these processes that happen, and that's called the weak interaction. And Fermi was the first one to formalize that. Beta decay, that's right, the beta decay of the neutron. Now, people did not, at this point, though, have a very clear understanding of what happened inside the nucleus. There were various speculations, but it was a very difficult problem. And as far as I know, this only came after the war, and substantially after sort of nuclear science had been put to use in the form of fission.
Secondly, Heisenberg never seemed to know about the
Right.
to get the bomb to work. And how come they couldn't find it?
So very good. So the question is about the difference between slow and fast, and who was aware of what. In fact, it turns out, the Berlin crew, who also discovered fission, they tried both. They tried slow neutrons and fast neutrons, because, as everybody else, they had a source that would initially give them fast neutrons, and they had to deliberately slow them down to get slow ones. But they were, in fact, experimenting with both slow and fast, and they were very puzzled at first as to why having slow neutrons would produce a much larger effect. It was counterintuitive to them.
And Heisenberg never picked up on it.
I don't know about Heisenberg. So Heisenberg is involved in the German nuclear science program during the war, and it was never conclusively established, to my knowledge anyways, whether Heisenberg was consciously sabotaging the German efforts towards a nuclear reactor that would work and a self-sustaining one, or whether conditions in Germany were simply such that they didn't facilitate this type of research. Because one thing was clear, there were a lot fewer resources allocated to that type of research in Germany than it was in the US, by far. So after the war, when the Allies went into Germany and they tried to secure the evidence that the Germans had also been working on a nuclear bomb, they were quite surprised to discover that the Germans were way, way behind. So it was not a close race by far. It was totally different.
The other comment that Robert Anderson got poisoned his lungs with working beryllium.
That's right.
And later killed him.
Yeah, that's right. So beryllium is very dangerous chemically, especially if you inhale it. It's not good. Yes?
Yeah, Professor, I want to congratulate you.
I'm not a professor.
Okay, but whatever. It's amazing how you have brought this to the Fermi Institute, the greatness of the Fermi experiment here, and you've tied those knots together in such a remarkable way. I really congratulate you here.
Thanks.
Definitely as great as that James Clark, not Clark, I forget his name again, but anyway, the guy with the PBS program that called Connections, you definitely have lived up to it.
Very good.
I'm curious though, so Szilard was the guy who really first figured out the chain reaction issue. Was he the guy, and he's the guy that informed FDR about that, which you didn't bring in.
Very good. Very good. So Szilard had a lot of things to do behind the scenes. So there was, in fact, one slide that I cut out because I was going over time anyways. But it's true. Leo Szilard was very much cognizant of the fact that this was potentially a topic, even in the early days, that would grow to beyond science, and it could involve politics. So he picked up a bunch of his Hungarian friends, and he would have actually an investment banker friend of his drive them from Manhattan to Long Island, where Albert Einstein was having a house. And Szilard drafted a letter that they would present to Einstein, and that letter, of course, would be that famous one that he would send to Roosevelt. And Einstein agreed to sign the letter. Now, there's sort of a fun tangent to that story, which is Szilard dictated that letter to a young women stenographer at Columbia University, and she wrote it. She typed it out for him to then, take on the strip to Einstein. And the letter spoke about, the potentiality of weapons that are immensely destructive and very dangerous, and then the letter would end with yours truly, Albert Einstein. And that stenographer surely must have thought that Szilard is totally nuts, dictating a letter to her that, would bear the name of Einstein and would speak about, unspeakable things. So Szilard was, even if he didn't want to always be in the front row doing the dirty work, he was very much aware of his responsibility as a scientist. And that's what he did.
Did Hahn know that it could result in a bomb back in 1939? Did you know that?
That's a good question. I don't know. I don't know if he knew. To me, it's true. I've also heard the story that Szilard is often credited as the person who first had the idea of a chain reaction. But to me, it's not really. First of all, it's a very sort of poorly defined concept. What does it mean to first have an idea, right? You don't know what other people were thinking at that time and so forth. The best I could manage to figure out and sort of have evidence for is that it was simply one of those things that you don't find the beginning of, but that suddenly was there, and then everybody had known it all the time, so to speak. It was clear to everybody. And even if you weren't, as a member of the project, even if you were listening from Germany, if you will, and you were reading what is publicly available in the journals, and you were a physicist who sort of had some common sense, you could put the puzzle together. Okay, it was not sort of secret in the sense that it was totally impossible and very difficult to really come to that conclusion, right? All the ingredients were
Nobody could
exactly. Yes, that's what I believe. Around, very good. So they stopped at around that time. So I believe that paper of Fermi, Anderson, and Szilard showing that you got more than one neutron on average. This is one of the very last ones that went out, and all of the other ones. Say again. Then it went quiet. So around 1939, 1940, it went totally quiet. And then after the war, Fermi and company, they would then publish all the documentation they had amassed on the Chicago pile and so forth. So all of these would eventually go out and become public. And you can read them today. They would go into scientific journals, but after the war. Right. Yes. So Fermi, that's right. So Fermi was always a very thorough lecturer. And starting from his days in Rome, he would teach his students whatever he knew, and that would continue. Even during the Manhattan Project, he would constantly give lectures to educate his peers and fellow scientists. Yes, please.
So, as you've told this story, it's been a story of the release of neutrons and what happens to them in their progression as they interact with other matter.
Yes.
But when we think of the bomb itself that results from all this, we see that the result is a vast release of light and heat and God knows what else that I don't
Very good.
know. And what I'm thinking about is, so with the letter and all that, they were already thinking about the potential use of weapons.
Yes.
But I didn't see anything in this history of the motion of neutrons that explains what makes it go boom.
Very good. Excellent question. So in fact, the neutrons, they are the ones that do make it go boom, but they are not the ones that are providing the light. Okay, you could see that there is something that's explosive and that releases a lot of energy. And in fact, Fermi had seen it himself when they looked at their scope trees, right? They saw these many small little peaks, which is normal radioactivity that everybody had known and studied. And then there were these huge giant peaks, which was the fission, that was a lot more powerful than just a mere decay. Okay, it was clear at this point that there is something that is qualitatively more powerful than a simple radioactive disintegration. And that was the fission. Now to your question about what gives the energy, and what makes it go hot and become colorful and emit a lot of light, it is the other two elements. Okay, the lighter atoms that you create by splitting apart the uranium, lanthanum and barium or whatever they are, they move away back to back in opposite directions with insane velocities. And they are charged. Okay, and just like the alpha particles, very easy to shield because they are charged and they're bouncing around in whichever shielding material you put. Because these nuclei, they had protons in it, so they were naturally positively electrically charged, but they were much more so charged than a single proton because there were many of them. They would be easy to shield. In a sense, they would be shielded by the surrounding material. They would, effectively, they would cause friction. Okay, they would cause friction because they would constantly be bounced around back and forth by all of the other atoms in the remaining material that they were embedded in. And with this friction, they cause that material to become very, very hot. And when a material becomes very, very hot, it starts to glow and emit light. And this is what you see.
I don't know if you can go back one slide to Henderson. I think you got it there. I saw him in the 1970s. They were cutting down the elm trees on campus because of the disease, and he was out talking to the news media. So a certain tree that they sat under, I don't know whether to be outside and have the conversation secret or just that much, but it's sort of the atomic tree, and I've got a little sliver of the trunk of it. I read that Fermi, going on with how active he was, he would go down to the lumber yard down around 70th Street to get the timber to build the pile himself. He took some grad students with him, but he would do it himself, I read. If
Very good. Yeah, that's a very good. So, excellent question. Now it turns out that, okay, let me bring that graph back. So you can sort of see. So what is an explosion? Right? An explosion is something that ramps up from nothing to something that's very dangerous and very powerful in a very short period of time. Right? That's what an explosion is. It certainly just flies apart. Now, their reactor, or any reactor for that matter, had the property that it could not as explosively ramp up in power as a bomb would. Okay? And that has the reason that whenever a neutron enters a nucleus, it doesn't immediately split apart that nucleus, but it stays inside the nucleus, and then the nucleus wobbles and does its thing, and then sometime later it comes apart. Okay? That ensures that if there's too many neutrons that could effectively make it run away, it would not make it run away in sort of an instant, but it would just lead to that casual upwards trend that could still be dangerous if you let it to continue for a sufficient period of time, but it would not be in a moment's notice. Okay? So even if they didn't have a cadmium, they would still have the people at the top of the reactor pouring down the cadmium and such. If they didn't have any safety precautions whatsoever, that line would just keep going and the reactor would get hotter and hotter and hotter. And at some point, the graphite would probably start igniting and burning. Okay, that's what would have happened. But it would not have caused an explosion in the sense of a bomb.
So Compton was right in not telling the president.
Yes. Yes.
A comment about Heisenberg. There's a wonderful play, you may be familiar with it, called Copenhagen. They came out, I think, in the 70s or
Okay.
80s. I really highly recommend people view it on YouTube. And it's about the visit between Oppenheimer and Niels Bohr. And they address this issue of what he knew or didn't know. But the meeting actually did take place.
Is that the Ann Arbor conference? Like, I know that Bohr came to the US several times and then they had exchanges.
Well, no, Heisenberg went to Denmark.
Oh, I see.
To visit, and Bohr originally was a mentor of Heisenberg, and almost a father figure. But the play is very dramatic, but it's very, very interesting. But the consequence of the play was that a whole lot of people who knew Heisenberg and other people involved in it directly started to talk and write about what went on. So there is a lot known. And if you really are interested in what Heisenberg knew or didn't know or what he did, there's a wonderful YouTube video by a woman who summarizes all of this in great detail, and it's very, very interesting. But my question to you is, are you familiar, Heisenberg built his own pile.
Yes.
Small pile.
Yes.
And it blew up. And I don't remember why. I think he was using water.
So he was.
Calculator.
Yeah, so that's right. So he was using heavy water, in fact. So the Germans had their own reactor. I believe it was in a place called Haigerloch or something like that.
Yeah.
And they would have effectively a large underground cistern that they would fill with heavy water, and then they would sort of suspend the uranium into that water vessel on chains or something like this. This is what their arrangement would look like. Now, the reason why they needed heavy water is because, heavy water has hydrogen, so it is a nice moderator. But normal tap water wouldn't work because it would absorb too many neutrons. That's why they had to go with heavy water, which had already the neutron inside, so that's why it was heavier, and that's why it didn't want to absorb more neutrons. Now, I'm not familiar with the story of if or when or how it blew up. I can't talk much to that.
As a matter of fact, the Allies were onto that, and there was a heavy water plant in Norway.
Yes.
They did a
Which
covert operation on.
they sunk the ferry or whatever. That I think it carried some of that water. That's true. Yes. In fact, today there are still reactors that operate using heavy water as a moderator. The Canadians have them. They use, and the advantage being that you can use, in fact, natural uranium. You didn't have to process it and enrich it in the isotope that was actually useful for fission. While if you had a light water reactor, which is what most Western reactors these days are, then you had to refine the uranium and enrich it to some higher, percentage of fissionable uranium-235. Yes. Yeah. Go ahead.
So I seem to recall reading history once referencing the Heisenberg-Bohr meeting after the war, and the garbled in memory, but the story I seem to recall is that Heisenberg went up to Denmark to see Bohr and said, after the war, said, well, remember during the war when I told you that I was going to make it happen so that we didn't produce the bomb for the Germans, and he sort of was looking for Bohr to confirm that, and all he got was a big no comment. And another historical note is that I'm very familiar with Italian history and politics and whatnot. My understanding is that because Fermi was here doing the work on the bomb, while Italy was still in the war on the side of Germany, the Italians never forgave Fermi because that bomb could have been used on them. So just a little.
Yes. I mean, it's dramatic times. In fact, Fermi and many others were not American citizens when they were participating in that research. They were, still officially citizens of an enemy country, right? And still, they found themselves at the very heart of a critical program. It was, insane. Yeah. Okay, then I would suggest. Okay, last question.
Well, two things about Laura Fermi, Enrico's wife.
Yes.
She wrote a book. I think the title was "Illustrious Immigrants," about how the U.S. benefited from the many scientists who had to get out of Germany and Europe. But also, she, when we were still burning coal and converting to gas, she was in a high-rise building living, and she would look around the neighborhood with binoculars and report any buildings that were still coal.
I didn't know about that. Thanks for sharing. Okay, yes.
I didn't recall from my youth watching a movie about that Norwegian operation. It was called The Heroes of Telemark. It was an interesting movie about the sabotage act. In any case, though, I'm a semi-retired natural science educator. I worked out at the CERN Earth and Space Center, which is named for the last astronaut to walk on the moon. And there's something going on which I think is very, very worth everyone knowing about. Something related to our ability to mimic what Carl Sagan called nuclear winter. And there's this proposal out to mitigate climate change by mimicking aerosols, stratospheric aerosols, and injecting them into the atmosphere to mimic how a volcano can actually. Well, it turns out that if you do this, and it's in conjunction with another actual volcano erupting, maybe like Pinatubo, or worse yet, like Mount Tambora, a couple of centuries ago, you could have something coming on close to nuclear winter. Now, in order to get everybody to understand how dangerous it can be, there's a documentary out. It's on YouTube. It's been for the last 6 months. It's called "The Year the Sun Turned Black." Yes, YouTube. The Year the Sun Went Black, and you'll find out something that could really scare you. Because if they do this, implement this scheme, and something like that happens, as shown in this documentary, we're goners. I mean, it could be that bad. I don't understand how the government can possibly be considering doing this. Now that I'm with a scientific-oriented people, I want to get this across to you as bluntly as I can. This is really ridiculous to try and alter Mother Nature like this. It's one thing to do it, to alter it as a byproduct of something desirable to do, like have energy. But to deliberately tamper with it is just insane, considering what can happen. If something natural happens in conjunction with it. Remember, we're at the phase change in the molecular cycle where we switch over to glaciation. We're in a nice interglacial now, but we're in the phase change that goes over to glaciation. And this, if you get all these things combined together, and you go into
Okay, let's discuss this over lunch, I suggest.